Does anybody have anything different for the answers for these three preview activities? All right, well, that's a good sign. When you start a problem like number 1, and you look at the square root of 18 and the square root of 8, what sort of things do you think about to get to your next step? What sort of things do you try to consider to help you with the next step? Well, you came up with square root of 4 times square root of 2 for 8 and square root of 9 times square root of, so you came up with this factorization for each of these, right? So why did you pick square root of 9 times square root of 2 versus, say, square root of 6 times square root of 3? Because you can find the square root of 9 is a perfect square. You can take its square root, right? So what you're really doing is you're doing a process of elimination in your mind, right? You're looking at the square root of 18, and you're really thinking about its factorization. Well, 18 times 1 doesn't help you because that's how you've started. If you do square root of 6 times square root of 3, there's nothing there that helps you. Square root of 9 times square root of 2, square root of 9 is the ding, 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 right? It's 3. And now earlier I had mentioned to you to look for a common factor. So for example, 2 goes into 18 and 2 goes into 8. They're both even numbers. So if they were going to be combined, they would have to have that like radical. So that's always a great place to start. It doesn't mean they'll have like radicals, and sometimes all you can do is simplify each of these radicals and you won't be able to combine them. But in this case, they both have square root of 2, and once you hit square root of 2, you're very happy to see that you have a perfect square multiplying the square root of 2, and you have a perfect square multiplying the other square root of 2. So 3 square roots of 2 minus 2 square roots of 2, now that they're like, you can subtract them and you get 1 square root of 2. Okay, originally this was written this way, like that, and that's okay. But as you can see, it's sometimes a little confusing, and if you happen to not have the neatest handwriting in the world, what might that look like? Square root of 23. So it's always a good idea to put any factor multiplying your radicals in front of it, and that's going to be important today. Right. The other thing I want to point out is this property. I'm just going to erase everything here. Is this property that we used here? We just said that the square root of 9 times the square root of 2 is equal to the square root of 18, or vice versa. The square root of 18 is equal to the square root of 9 times the square root of 2. And this really comes from our exponent properties, because every square root can be written as the exponent 1/2. So if you had 9 times 2 to the 1/2 power, this is a product inside. This really says the square root of 9 times 2, or the square root of 18. Remember, when you have two factors raised to any power, the power comes down and kisses each one of them, right? So this becomes 9 to the 1/2 times 2 to the 1/2, and in radical form, that looks like this. Okay? So we're feeling pretty comfortable with that. But what you have to realize is that all of these properties are for real numbers only. Okay, for real numbers only. And you might say, well, what the heck, what other numbers are there? We're going to explore that today. So what you're used to doing here, especially with this multiplication, is no longer going to be true for the set of numbers that we look at today. It's only true for real numbers. Okay, the next one, yeah, Elliot? Streeter, I'm sorry. It was 1 square root of 2, or square root of 2. Did you get that? Okay. All right, so I had partially erased here my question. This is correctly factored. You took this adding and subtracting problem that had 1, 2, 3 terms, and you've expressed it as 2 factors. Again, what you need to get out of your mind is that this is the only way to factor. This is what everybody thinks a factoring problem looks like. Remember, sometimes all you can do is pull out a common factor and multiply the expression. That's the remaining expression once you pull out that factor. So don't always think that this is the only way to factor. So my question here is, how do you know if this is right or not? What can you do before I come along and tell you whether it's right or wrong? Yep, Beth? The what method? The box method to do it, but how do you know your answer is correct? Okay, and what does, when you do this with your hands backwards, what are you doing? Yeah, the 2x times the x, the 2x times the 4, that's your distributive property, and then your distributive property again. So you're using your distributive property twice, and you get 2x squared, you get negative 1x in the middle, plus 4x minus 4, and these two can combine because they're like, oops, that should be 8, 2x squared plus 7x minus 4. Okay. And then we don't see the work for this, but unless I hear from anybody, I'm going to just let it be. Do I hear anything from anybody in terms of questions on this? Any questions on this? All right, we'll leave that. Okay, so here we go. I love this little cartoon, the square root of negative I with that face saying, do I really exist? Mathematicians way back, I don't know, I can't remember if it was the 15th or 16th century, they used to have competitions for solving equations. You know, you have to realize way back then how less developed, at least compared to what we have now as a body of mathematics. So they came across an equation that they couldn't solve with real numbers. So they invented, everything is invented in mathematics. They invented a number that would solve this problem, and it isn't a real number. Sometimes it's fortunate that they're called imaginary, because then you think that they don't exist, but they do exist. And we use this definition because we've always been told you can't take the square root of a negative number, and that's true in our real number system. But with our new number system, we use the letter I to represent the square root of negative 1. And one of its most important properties, where I square is equal to negative 1. So if you square I, you get negative 1. Okay, so this is a pretty critical and important, both of these are important properties that you need to know for the rest of today, or actually the rest of your mathematical education. And I think you've probably seen this along the way. So if k is a positive real number and you see the square root of the opposite of some real number, then you can factor out the square root of negative 1 times the square root of k. And then you call the square root of negative 1 I. So it's always going to be I times the square root of whatever the real number part of that is, whatever k is. So for example, the square root of negative 49. Now, I want you to be aware that this symbol right here is asking for the principal square root. That symbol always asks for the principal square root. And what do I mean by the principal square root? That's a good guess, the lowest you could go. That symbol means something. All right, so let's suppose I do this, square root of 9. What is the answer? 3. And why isn't it negative 3? Because negative 3 squared is 9. Jameson? Simplest, lowest, we're almost there. Okay. So if we put a sign on it, we call it negative. So without the sign, we call it positive. So that symbol, the principal square root, always indicates, because we have two square roots for a number, so it always indicates the positive square root, right? The positive square root. You put a, how would you indicate the opposite, which is the negative 3? What would you do to this 3 to make it the opposite? No, that's not opposite. How do you write the opposite of 3? How do you write its opposite? Yeah, and how would you write that? Here's 3. How would you write its opposite? What would you do to it? Put a dash in front of it, right? I'm getting there. Okay, just be patient with me. So to get the opposite of this, I put a dash in front of it, right? To get the opposite of the principal square root, I put a dash in front of it. Okay, so when you see this, it indicates the positive square root. When you see this, it indicates the negative square root. Okay. All right. So sometimes I ask a bunch of questions, but I am getting to your question. You just have to bear with me. All right. Bear with me. I wonder where that saying comes from. Anyway, all right. So the square root of negative 49, when you see that, you want to write this as the square root of negative 1 times the square root of 49. Okay, you want to factor out the square root of negative 1. We know the square root of negative 1 is defined to be this funny thing called I. It's in an imaginary unit. We call I the imaginary unit, a number. Okay. And so we put I, and we put it in front of the radical to start with, and now we have I times 7. So if your square root is a perfect square, then it's okay to put the I in front or before. But if this was like the square root of 13, you'd want to keep the I in front. So we don't have that misunderstanding about where is the I? Where does the I belong? Like with the square root of 2 times 3 that table 1 just wrote up. Okay? Okay, so try the next one at your seats, B. Try B at your seats. Well, first of all, we've got to replace the square root of negative 1 with what it represents. What does that represent? Square root of negative 1. I. So right now I have I times the square root of 20 times another I times the square root of 5. Okay, so this is a multiplication problem all the way across. I'm going to use my commutative property to rearrange my factors because I'm allowed to do that in multiplication, and I'm going to put the two i's, the two factors of I, right beside each other, and then the square root of 20 times the square root of 5 right beside each other. And now I'm okay. I times I is I square. Oh. And the square root of 20 times the square root of 5, that's okay to multiply because those are positive numbers. So now what do I have? Yep. Can we do that once I finish this? We'll take a, I think they should both come up the same way, Jameson. So let's see how they do that, okay? So I square, what did we define I square to be? Negative 1. And what square root of 10 am I looking at here? Positive square root of 10. I mean, excuse me, I gave you the answer. Square root of 100 is 10. So this is negative 1 times 10, which is negative 10. Okay. So that's the only thing that's a little bit different than what you're used to. Let's take a look at what Jameson wanted to do, because regardless of how I factor each of these numbers under the radical, I should get the same answer. So Jameson wanted to write this as the square root of 4 times the square root of negative 5. And then what did you want to do with the negative? Yeah. Oh, I'm sorry, Jake. Sorry, Jake. Thank you. Jake. And then what did you want to do with the square root of negative 5? All right, so can I write this one as negative 1 square root of 5? Yeah. Okay, so then you call the square root of negative 5 square root of negative 1 times square root of 5. And then this one is the same, square root of negative 1 times the square root of 5. Okay, so Okay, well, let's see. Square root of 5 times the square root of 5, that's the square root of 5 squared. And remember, if you look at this as exponents, it's a little easier. These two become 5 to the first power. These are inverse operations. Or you could multiply it out and say the square root of 25, however you want to do it. But the point is, when you multiply a square root times itself, you get the number that's under the radicand itself, I'm sorry, 5. So this is 5. Okay, because each one of these really represents the sides of a square whose area is 5. Because remember, the side of a square is the square root of the area. All right, so we know that this times this, they don't cancel each other out. They just become 5. So when we multiply these two, we get the number 5. What happens with the rest of it, Jake? So the square root of 4 gives me a 2. So far I got 10. And then what do I get? Right. So the square root of -1 times the square root of -1 is -1. And I get -10. So regardless of how I choose to factor these radicands, both of them will give me a -10. All right. So you should feel comfortable doing it any way you want. Okay. Again, the key is that square root of -20 times the square root of -5 does not equal the square root of 100. That's the key idea. Okay. So linear equations, we know, we've talked about, have a highest power on them, a highest exponent of 1. Quadratic equations are second degree equations, which means as you look across your entire equation, the highest power you see is 2. And what I always try to encourage my students to do is when you look at a quadratic equation, you should always put a little highlight on that exponent just to remind you that you may possibly have 2 answers. Unlike a linear equation where you could have 1 answer, okay? At most 1 answer. So that's the language we use. Here, at most, you have 2 answers. Sometimes you could have no answers in the real number system. But once we expand to this new system we're going to talk about, we can get 2 answers. Okay, so in general, we say this is the general form of a quadratic equation. Notice it looks very similar to our linear equation. The general form of our linear equation looks like this. Notice we only had to use 2 A's, an A and a B, because we only have 2 terms. Once we get to the quadratic, we have to use an A, B, and C. If we had a cubic equation, what letters do you think we would need to represent the coefficients? If it was cubic. You know what degree cubic is? 3. Cubic is like a volume. A, B, C, and D. Right. So if you had a cubic equation in general form would look like this. AX cubed. So we're using the A to go with the x cubed. And then B would be with the square, and C would be with the linear term, and D would be the constant. So even though A and X, A, B, C, and D and X are all variables, we often, I don't know if you've noticed this, we often use the letters at the beginning to represent the coefficients. All right, little tidbit, not really important to your education other than it's something to notice. All right, so we're familiar with the techniques to solve linear equations. So let's use some of these techniques and find other ways to solve quadratic equations. So one of the things I want to point out right at the beginning is that all quadratic equations, no matter what form they have, can be solved with the quadratic formula. However, sometimes it's much easier and simpler to solve it with one of the techniques I'm going to show you now. Okay, but you have, I don't care which technique you use. I was talking about this with Ian yesterday, and he said, well, in 096, we make them use different methods. And I said, I understand that. I don't care if you just use the quadratic, but you better know how to use the quadratic formula correctly. I've seen more errors with that than one of these methods here. So first of all, I just want to point out to you the different forms that a quadratic equation can take. So this was the definition of a quadratic equation where it said a could not be 0. And the reason why a can't be 0, because if a was 0, this would disappear and you'd have a linear equation. However, b could be 0 and c could be 0. So for example, you could get a quadratic, let's look at a quadratic equation, not c, where b equals 0, sorry. All right, so let's take a look at this. 2x squared equals 8, for example. And that can be written in that form, or if we set the whole thing equal to 0, it would look like this. Okay. So in this case, when b equals 0, there's a couple of approaches to this. Okay. One approach is to just solve for x squared on one side and your constant on the other. So I would divide both sides by 2, and I'd get x squared equals 4, and here's where the trouble spot comes in. A little bit of trouble. Because most people will use what we just talked about 5 or 6 minutes ago when Jordan was asking me about the principal square root. Okay, if you do this, if you put this on each side like that, you're setting yourself up for an error, because that symbol only means the positive square root. So you're going to write x equals 2, and you're only going to get, remember what I mentioned to you, you're only going to get half of your possible solutions. Okay? And we talked about this earlier in the semester when I said it's not your fault because, you know, along the way, teachers never really asked you to do this. I'm going to give you, again, the real reason why this answer has a plus and minus. You probably will ignore it and skip it. But the most important thing is that you understand that it has two answers. Again, I would, if you've tended along the way to make this mistake, I would just, I'm going to give you your little toolkits today. I would highlight this every single time I do this. And when you write this, this goes back to our very first class where we were looking at absolute values. The square root of x squared, because this is asking for the positive square root, you can't just write x, because get out of your mind that that x is a positive number. We have no idea what this x is. It could be 2 squared or negative 2 squared. Okay? It could be any real number. So once you put this around it, just like once you put the absolute value around a variable, you have two possible answers. So, excuse me, two possible values for x. Right now you have two possible values for x, but once you put that square root around it, you have one possible value. That's what I meant to say. It's only the positive. So you can't write this because x here could be positive or negative. You have to do this. Now this really says the positive square root of 4, which is 2. But this is what was left out. Books get out of this easy by saying every time you see a problem like this, then you write your answer like this. All right, fine. Plus or minus 2. That's not hard to do. It's not hard to write in a book. But there's no explanation of why this is happening. And there's no explanation for the person who does this to just write x equals 2. Why am I wrong? Because you haven't been really, you really haven't conceptually agreed that when you look at this x, you don't see it as a negative number. You just see it as positive. And that's where you're setting yourself up for this misconception. This is really how you go from this equation to the next step. Now, when you look at this, you know from your definition of absolute value, what number can go in there so that the distance between 0 and that number is 2. What numbers can go in here? 2 and negative 2, right. So now you say, well, if the absolute value for x is 2, then my answer has to be plus or minus 2. I can put a negative 2 in there or a positive 2 in there. That's a long answer for this, but it's so critical to your conceptual understanding of what's really going on. And for some of you, you'll just blah, 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 I'm up here talking, and you'll train yourself to do that, and that's fine. Okay. Now, another sure way to get around this, where you don't even have to think about all that, is anytime you have x squared equals a number over here, it doesn't have to be a perfect square. Set it equal to 0. Set it equal to 0 and factor it. Anytime you're missing your middle term, the bx term, you take the square root of each of those, plus and minus, and you're done. This way you are absolutely going to get two answers because you use the zero principal rule. You say, when is this factor 0 and when is this factor 0? This factor 0 when it's -2, that factor 0 when it's 2. So again, you can see there's a couple of approaches to doing these, right? Key here is that there were two solutions to that equation. All right, so that's this this business here now is what if we have x squared equals -25? Well, before we would have just skipped it and said, no, we can't do it. So in this case, x is going to equal plus or minus the square root of -25. So off on the side of your paper, because -25, just like the number 25, has two answers. So you just don't want to put the positive radical in front of it because that's only asking for the positive one. So when we look at this, plus or minus the square root of -25, you do what we just did a minute ago. You pull out your -1 and you get plus or minus I times 5. And usually when we have I times an integer like that, we write plus or minus 5i. And again, check yourself. 5i, when I square that, I should come up with -25. So let's see. 5 squared and I squared. 5 squared times I squared is 25 times -1 is -25. That works. Let's try -5i squared. That's -5 squared times I squared, which is 25 times -1, which is -25. So as you can see, when you have to find the square roots of -25, you have two answers: positive 5i and -5i. Jordan, do you have a question? Okay. Did it get answered? Okay, good. All right. The zero product principle or property is what we just used a few minutes ago. That is, factor your equation once you set it equal to 0, and then you set each factor equal to 0. So let's do this one. Now notice that this quadratic equation, when I set it equal to 0, has a value for a, that's the coefficient of x squared, which is 1, a value for b, and a value for c. Okay? So in this case, we're looking for factors of 24. Factors of 24. I don't use the box method. Of 24 that add to 11. So you look at your factors of 24, and the two factors of 24 that add up to 11 are 8 and 3. So I put my two sets of parentheses for my two binomials, and I put an x and an x, an 8 and a 3, a plus and a plus. And now this zero product property comes in use because this acts like A, this acts like B, and when I multiply two numbers or two expressions that equals 0, one of them is 0 or both. Sometimes they both can be 0 if they're duplicate factors, right? Like x plus 2 times x plus 2. So in this case, you set each factor off to the side and set it equal to 0. And notice it's just a baby linear equation to solve. You subtract 8 from each side. There's your first solution. And then you set your second factor equal to 0, subtract 3 from both sides, and there's your second solution. Okay, so two keys to this way of solving a quadratic equation. First and foremost, this principle only works when you have 0 on one of the sides of your equation. You can't do this equation with a constant over here or any of these terms. So you get all your terms on one side and you set it equal to 0. So the one situation we haven't looked at is we've had b equals 0 up here, b was 0, so we just had our quadratic term and our constant. Here we had all three of our terms, so the only one we haven't looked at is what happens if c is 0. So let's take a quick look at that. So if c is 0, let's take a look at one. 4x squared minus 4x equals 0. So what would you do to solve that? And this will always be true whenever c is 0. You'll always be able to use this method. What would you do with that? You can factor out the form. What else will always be true if c is 0? Jake? Yeah, you'll always have x common in both of them because you'll have your x squared term and your x term. You'll always have at least a common factor of x. So anytime your constant is 0, this is golden, okay? So you pull out your 4x and you have x minus 1 equals 0, and you're almost there. You can divide both sides by 4. You could have done that right back here if you wanted to and got x squared minus x equals 0 and then pulled out your x. It doesn't matter because a constant's never going to equal 0. So if you pull each one of these factors out and set it equal to 0, 4 never equals 0, so that's not part of your solution set. So you can either say 4x equals 0 or just x equals 0, because when you solve this, you get x equals 0. Then you take this factor, x minus 1 equals 0, and x equals 1. So those are your two solutions here, 0 and 1. Okay? So if you make a little sheet for yourself where you start off with this quadratic function and you put 2 or 3 examples down for yourself. Put an example down like this where c is 0, so you can remind yourself the GCF will always be helpful. Then give yourself one where you have your square and your constant, and you write a note to yourself. Don't forget there's 2 answers, right? Then you can do one with the full quadratic like we just did, and we can either factor it, and if it's prime and it can't be factored, then, or you can't factor it easily, then you'll want to use your quadratic formula, which is right here. All right. So we can memorize this very easily. When you're little, how is it that you can say the whole alphabet as a little young kid? Why can you say the entire alphabet if you grew up in this country? How could you say that so at such a young age? What is it that helps you with that? The song, you sing it right. A, B, C, D, E, F, G. Right? So we can sing the quadratic formula too. Right. Squared minus 4ac all over 2a. Guarantee you sing that to yourself a couple of times, you'll never forget it. Oh God, I know. All right. So again, let's take a look at solving the quadratic equation, and then you'll have a half an hour or so, 25 minutes to work on these activities. Here's a quadratic equation, the full-blown quadratic equation, right? The full Monty here. So you say, well, can I factor it? Are there factors of 7 that differ by 6? Are there factors of 7 that differ by 6? What are the only factors of 7? It's a prime number. 7 and 1. Do those two numbers differ by 6? Okay, we're set. We can factor it. But x minus 7, x plus 1, boom, I'm done. See how quick and easy that is? X is 7, x is negative 1. However, we want practice with the quadratic formula, but at least we know what our answer should be right now. So let's use our quadratic formula here. Again, if I were doing this, I would have just factored it. But I know some of you have this like aversion to factoring, so we'll do it with the quadratic formula. So we need to identify each of the letters. Let me point out, is that an equation? X equals, right? It's an equation. And remember we talked about when we wind up with our final equation looking like x is a number, that everything that preceded it was an equation. You know, I have a couple of little things that really bother me. And one is when people leave off the x equals, when they start with an equation and then they just drop off the x equals. Okay, so when you start, you notice you're starting with an equation. When you go to the quadratic formula, it is another equation. You're solving for x. Please put that on. Okay, x equals. Then from this point, you can just keep writing equals, equals, equals. You know, you can be a little lazy. That's okay. I do it too. So let's see, the opposite of b, well, b is a -6. Let's identify each thing. B here is a -6, a is a 1, and c is a -7. So the opposite of b is 6 plus or minus the square root. And if you're going to put b in and it's a negative number, it must be in parentheses. Why? Because this does not equal this. This says -1 times 6 squared, and this says -6 times -6. This is -36, and this is 36. If your base is negative, it must be in parentheses. So whenever b is negative, you have to have parentheses here. Minus, and then I always put 4ac in brackets like that to help myself. Why? Because if this quantity in here is negative, sometimes the mistake is that you use a subtraction to take the place of that negative number. So this way, if it's in parentheses, you'll see it. So I have 4 times a times c, which is -7. The entire thing, so that fraction bar goes over the entire numerator, under the entire numerator, 2 times 1. Okay, now you can do this, equals, or I just go down to the next step, x equals. So let's see, let's simplify this. 6 plus or minus the square root of 36, take away. Now what's in those parentheses is a -28. So see, you want to make sure you have 2 separate dashes there. One dash means the opposite of 28 or -28, and the other one means subtraction over 2. So this is 6 plus or minus the square root of, what do we have here, 64 over 2, which is 6 plus or minus 8 over 2, which is 6 plus 8 over 2, and 6 minus 8 over 2. My answer is 7 and -1, which matches my factoring. Okay, so you'll have some more work with complex numbers and some more work with solving quadratic equations. Okay, you have 22 minutes, so look around at your problems, do the ones that you think may be more challenging to you. Okay.